last two videos, we consider some nested radical. There is a first expression here and the second expression there. And today we are going to consider continued fractions, that is, this form. What will be the value for these continued fractions?
Pause the video now if you wish to solve it. Keep watching the video once ready.
Some claim that 3 is equal to 7 minus 4. And 4 can be written as 12 over 3. That's correct. And then the 3 here can be written as 7 minus 12 over 3 again. So this process can be continued because this is a 3 and 3 equals to 7 minus 12 over 3. It seems that this is reasonable to write it as many terms as possible. So based on this, some claim that this actually equals to 3. But we can look at another possible answer. That is, I start with 4 and say that 4 equals to 7 minus 3. And 3 equals to 12 over 4. And we do the similar thing here. 7 minus 12 over 4. 4 equals to 7 minus 12 over 4 again. So this will be 12 over 7 minus 12 over 4. 4 equals to 7 minus 12 over 4 again. This can be written in this form, and we can repeat it as many terms as we like. So in this case, we will say that, hey, this expression will be equal to 4. But previously, we just proved that this expression is equal to 3. Does it mean that 3 equals to 4? Definitely not. Then it must be something wrong. We ask a fundamental question now, that is this expression even has a value? If it does, what is the value? Is it equal to 3 or equal to 4 or something else? It is similar to the expression that we have in previous video, that the nested radical can be written as 3 or 4. In order to get the answer for this expression, we will define a sequence. And this A1 is equal to 7. So the first term will be just 7. After that, we will cover everything here, and you have 7 minus 12 over 7. And A3 will be 7 minus 12 over 7 minus 12 over 7. So A1, A2, A3, and so on and so forth. In short, we'll just define A1 to be equal to 7, An plus 1 to be equal to 7 minus 12 over An. All these can be replaced by A2. And this one can be replaced by A1. So if it's An plus 1, this can be replaced by An, where n is greater than or equals to 1. For this expression, it is actually the limit of An when n is big enough. When n is big enough, either An or An plus 1, they are both the same. Suppose that the limit exists and the limit is equal to L. Then this will be equals to the limit of n go to infinity. An plus 1 is 7 minus 12 An. And this is equal to limit of An when n go to infinity. We do a little bit of calculation, and this will give me 7 minus 12 over L equals to L. Then 7L minus 12 equals to L squared. L squared minus 7L plus 12 equals 0. Then L minus 3, L minus 4 equals to 0, L equals to 3 or L equals to 4. Suppose the limit exists either 3 or 4, which we already know just now. So how are we going to determine whether the answer is 3 or the answer is 4. So in order to get the answer, we claim that an is always greater than 4. And we will prove this by induction. When n equals to 1, a1 is equals to 7 and it is equals to 4. That is correct. Suppose that ak greater than 4, some integer k. Then ak plus 1 will be equals to, according to this relation, 7 minus 12 over ak. This will be greater than 7 minus 12 over 4. And this is exactly equals to 4. ak greater than 4 will imply that ak plus 1 greater than 4. And since a1 is greater than 4, then by mathematical induction, ak is greater than 4 for all positive integer n. an is greater than 4 for all positive integer n. L cannot be equals to 3. Note that the statement says that an is greater than 4 for all positive integer n. But right now, n is tend to infinity. It's just like we say that the limit of 1 over x when x go to infinity is equals to 0. But when you check 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on and so forth, each of this is greater than 0. The limit of 1 over n when n tends to infinity, we say that it is equals to 0. When n is big enough, we will say that this is equals to 0, although each of the term is more than 0. Next, we have to show that an is always decreasing. That is, an plus 1 will be less than an for all integer n. So we will consider an plus 1 minus an. An plus 1 it is 7 minus 12 over an minus an. This is 7an minus 12 minus an squared over an. This can be simplified as an minus 3, 4 minus an over an. Since an is greater than 4, an minus 3 is positive and an itself is positive. But 4 minus an will be a negative value and therefore this is negative. An minus 1 minus an is negative. It means that an plus 1 is less than an, and we just proved that this is true. So if you look at the graph for an, so it will be decreasing and very close to 4. Therefore, we say that the limit of an when n go to infinity is equal to 4. Indeed, you can see that the value of an is decreasing and go to 4. We can view this question as an iteration where xn plus 1 equals to fxn, where fx equals to 7 minus 12 over x. As long as the initial value is not equal to 3, then this value will always give you a 4. It is only fail when x0 equals to 3. Hope you enjoyed this video. See you next time.